Right. We will look at the principle of maximum likelihood estimator. I will explain the idea behind it and then go through some examples. So to start with, we have some unknown parameter that we want to estimate. It's a non-random parameter. It's simply unknown. And obviously, we collect some data that's related to this parameter. So this is the data that's collected. So data is always the truth. So how do you collect the data? Which data is relevant? All these are good questions, and for another time. In any case, we collect the data, and also it's reasonable to assume that it may not be always true. Whenever possible, we'll try to make this data independent of each other. In other words, the samples are independent. In a common sense ways, that makes sense. Because if you simply collect data that is, in other words, in the worst case, if you simply repeat the same data, that's not giving you any more new information. You can have correlated data, but of course, in our case, if the samples are independent, then their joint description becomes easier. In any case, data is you collect it in real life, so it's not going to be deterministic quantities. It's reasonable to assume that the data is random. So if that's the case, they have a joint density function, x1, x2, xe, etc., xn. That's where we start. And also we know that if you collect data sensibly, the data has to have something to do with the parameter. So we can also assume that this joint density function is a function of theta implicitly. And here, the only unknown is this quantity, so I can also write it in this fashion. And because the data is, of course, measured quantities, these are all given. Once you make the measurement, you have you can just substitute them here. But it is true, from the context they have, depending on the noise and other uncertainties or the problem itself, they have a joint description, but we have already assumed that the data samples are independent. So in our case, this joint density function becomes the product of the marginal density functions. And this is where we start. So this this formulation is due to Fisher, the father of statistics, last century. So we also will call this the following the usual terminology, the likelihood function. A likelihood for, I guess, for theta. It's going to tell you something about the theta, because everything you need to know about theta that is contained in the data is captured by this function. So that's the likelihood function. This is all we have, and we have to work with this. So one question is, you need to know the density function. Of course, you don't know the density function. You have to go back, step back, and try to estimate that, and so on. So we'll start with the simple case. We'll assume that we know the joint description of these random variables, which only has one unknown once we make the measurements. So of course, if the measurements are sloppy, then this whole thing gets sloppy. So that's where the art of designing the experiment, what to measure, how to measure, etc., comes in. So let's say we went through all this, and we are here. So we have the joined description of the measurements, which has something to do with, obviously, the parameter that we are looking for. So then the Fisher's idea is, this being the entire information. Notice here, as I said, if you look at this function, there is only one unknown. And after all, this is a probability function. It's telling you the likelihood, etc., of something being somewhere. So I can plot this as a function of xi's and theta, but xi's in this case are given because we have just made the measurements. So there's only one parameter to unknown parameter, that is theta. So I can plot this density function in terms of, and this is being a, of course it's a density function, so it's a non-negative function, so it's to be something like this. Area under the joint density function on all these variables must be 0. In any case, you can, not on theta, on the variables x1 through xn. But in our case, we have made measurements, so these values are fixed. It's only a function of theta. That's why we use a term as likelihood function rather than the joint density function, because the area under this is not 1. But this, nevertheless, this being a probability density function, it is telling something about the theta. So what it says is, given this data, so we could interpret this function saying that this is the peak corresponds to the most likely value of theta suggested by the data, by the specific data. So this is obviously a value of theta. So the most likely value, most likely because that's where the probability density function peaks. This is where the function peaks. So this value of theta has the maximum probability, because if I take a small region around that, this one is more than taking such a similar strip anywhere else. So most likely value of theta suggested by the current data. So of course, if you make different measurements, you will have different value. So that's the principle of maximum likelihood. In other words, you get the joint density function, call it the likelihood function, and then look for the value of theta which maximizes this function. Sometimes it's also convenient to write it in terms of the logarithm of this likelihood function. So we'll use a difference number, lambda. So that also has a nature like this, because its logarithm is monotonic with the parameter or with the variable for positive values. So again, you will get the same theta hat. So we'll call it theta hat ML, indicating that it's the maximum likelihood estimator. And we'll also show it like this, showing that it's a function of x being the data that we have just measured. So basically, the principle of maximum likelihood is simply look for the maximum value of the joint density function so look for maximum of L of theta, which is the same as the joint density function of the data. Of course, as I said, the data is given, so there's only one parameter, theta. Or sometimes you look for the lambda of theta, which is natural logarithm of L of theta. So of course, this is a smooth function. One way to look for the maximum value of this function. So one way, if this is smooth and well behaved without discontinuity, etc., one easy way to do this is simply take the logarithm of the log likelihood function or the likelihood function with respect to theta and equate it to 0, and where the solutions will correspond to maximum likelihood estimators. This is easy to say. So as you can imagine, there's no reason offhand to say that the solutions will be unique, etc. So that's true. Maximum likelihood estimators this equation may have multiple solutions, but we look for the maximum peak. Even that need not be, you can have the two peaks of the same value, so it need not be unique. So this is where we sort of start and where we end also. In other words, there is nothing more in terms of the principle. Of course, in some cases, if the data is measured data, if they are not independent, then this you have to deal with the joint density function, which is a bit more complicated. So the best way to, another way to reinforce what I said is through working out few examples. So let me do that. I'm going to take the case that the data happens to be Gaussian, and what we Gaussian has two parameters. And let me take the first case where the mean is unknown. So expected value of xi or is mu, but this is unknown. So mu is unknown, the mean value of something is unknown, let's say the temperature. So we make some measurements, x1, x2, etc., xn, here and there, maybe in different parts of the city, so that these observations are all independent. The question is, how do you use this to come up with the value of mu? So I'm going to put a hat for estimator. So this is an open problem. Maximum likelihood or otherwise, how do you get an estimator based on the data? I haven't discussed any properties of the maximum likelihood estimator. So in general, we could put it like this. If I put a suffix here, that's going to be maximum likelihood estimator. So let's concentrate on that. So I need the joint density function. So we need f1, etc., xn. So they being independent, these are the product of the density functions here. So that's going to be 1 over square root of 2 pi sigma squared e raised to minus xi minus mu the whole squared over 2 sigma squared. And if I involve this product, that's going to be 1 over 2 pi sigma squared to the power n by 2 e to the power minus. This product will appear as a summation here, xi minus mu the whole squared over 2 sigma squared I equal to 1 through n. So let me take the logarithm of this. So lambda of theta is logarithm of f of x1, etc., xn theta. So notice lambda of this is a constant. So the action is here. I'll write it in the next page. So lambda of theta would turn out to be a minus n by 2 log 2 pi sigma squared. This is natural log minus 1 over 2 sigma squared summation xi minus mu the whole squared I equal to 1 through n. So here, things being well defined and smooth, we can take the derivative. And there's no derivative with respect to mu, of course. Parameter is mu. There's no mu here, so the partial derivative is only here. So the minus 1 by 2 sigma squared is a constant. Summation I equal to 1 through n. Xi minus mu with a 2 and then a minus 1. This should be equal to 0. So we can solve for, we get rid of all the constants. So this gives you mu hat ml equal to 1 over n summation of xi I equal to 1 through n. I just take the take the mu terms to the other side and solve it. So this must be the maximum likelihood estimator. So this is the standard mean. You just add the values and divide by the total number of observations. This is what we would do in any case to find the average. So now what? So how do you know that these are good estimators? What are the other properties? So what could we say further? So at this point, you can see that, of course, the whole idea is mu is unknown. And in place of mu, we get, this is going to stand in place of mu. So we would like this quantity to be as close to mu in some sense as possible. So how do you express that feeling? So this is where the principle of the notion of an unbiased estimator comes up. So this is like a wish list. We want an estimator. Remember, this is a random variable. This is not a random variable. Nevertheless, we are using a random variable to represent a non-random variable. And this is random variable because data is random. So estimator is certainly random. So one thing we could say that expected value of this random variable must be equal to what we are looking for. This is how we capture some of our feelings on this on the properties of the estimator. So we are going to make this random variable as a representative for mu, a non-random variable. So at the very least, one way to express is that we want so this is in general, this is the property of an unbiased estimator. Any estimator, if the expected value of theta hat equals theta, then we call it an unbiased estimator. So another desirable property is that, of course, if you want a random quantity to look like a non-random quantity, its variance better be small. So you could also say that the variance of any theta hat desirably, this is an estimator, should go to 0. And we can, or at least become smaller and smaller with n. If you give more and more observations, this is another desirable property to have. So this is consistency. I think, with the estimator becomes consistent with the parameter. So we can try to see whether any of that is true for our estimators, for maximum likelihood estimators, etc. So again, to start with, we can see there is no reason to believe that all maximum likelihood estimators will be unbiased or something. So let's go back to our problem. We have theta hat mu hat ml equal to 1 over n sigma xi, I equal to 1 through n. So we want to find out its mean and variance. So now I'm going to use some certain things that we learned in probability. So notice that xi's are to start with normal with the mean mu variance sigma squared, and xi's are independent. So if you add a bunch of normal or Gaussian random variables, you get to normal. Its mean is the sum of the mean. So sum of the mean is n mu divided by n. So that's also mu. And its variance is the sum of the variance of the sum of random variables, independent random variables, is sum of the variances. Each variance is sigma squared. So the variance of sigma xi is n sigma squared. So the variance, you have a constant, the constant squares, because variance is square of the random variable minus mean squared. So 1 over n sigma squared over n squared. So the variance is, you can work it out, sigma squared over n. So actually we worked out the mean here. We know that the mean is sigma is mu. So this is unbiased. It's an unbiased estimator. This is an unbiased estimator, and it's a variance of mu hat ml. You can work it out anyway. I have it here. So also we see that it goes to 0, because as n becomes large, it goes to. So that's a good property to have. All right, let me move on and do a few more problems. If you notice, now the normal has 2 parameters. So let's assume in the next case that the other parameter is unknown and see what happens. So let's redo the same problem. And so I'm just going to, so here the unknown is this. So I'm assuming that mu is known. So once again, just copying from the previous slide, we had the likelihood function as remember here sigma squared is the unknown. So I'm going to rewrite, I'm going to call sigma squared to be theta so that we can see what is going on. So I'm going to simply rewrite this as log 2 pi plus log theta minus sigma xi, because it will be easy to do the derivative with respect to theta. Just so let's do the derivative with respect to theta. So here you get minus n by 2 theta minus sigma xi. So this is a constant because the derivative is with respect to theta. So this becomes 2 theta squared equal to 0 at theta equal to theta hat ml. So take this term to the other side and solve for theta hat ml. That turns out to be 1 over n sigma xi minus mu the whole square. Remember, I am considering the case where mu is known. If mu is unknown, then we have two parameters and we have to deal with that separately. So let's do simple things first. So again, this is what we get. Since mu is known, let's say mu is 0. So this is everything is known on the other side, on the right side, because xi's are known. This is just data. So this is the maximum likelihood estimator for variance, not sigma, but sigma squared, when that mu is known, when the mean is known. So let's see what is it, whether it's unbiased or not. So expected value of theta hat ml is 1 over n summation expected value of x. Expected value is only on the random variable. So just here divided by 2 sigma squared theta I equal to 1 through n. But notice this quantity is sigma squared by definition. So this turns out to be n sigma squared over through the summation n sigma squared. Then there is an n here. Okay, so there was no reason to put this. Notice that this is the estimator. So I'm just taking the expected value of this. So it's going to be expected value of this, which is sigma squared, n sigma squared over n. So that's going to be sigma squared. So expected value of the maximum likelihood estimator for sigma squared is unbiased. In other words, this estimator is also unbiased for sigma squared. So next question is what is its variance? So we want the variance of theta hat ml. Variance of any random variable is its expected value of the square minus the expected square of the expected value. But this we already know as sigma squared. So this is expected value of theta hat squared minus sigma 4. So we want to find out theta hat ml. So we want to find out this quantity. Theta hat ml is here. So let me do it here. Theta hat ml is 1 over n summation xi minus mu the whole square from the previous page. So I just copied this last line. So now we want to square it and take the expected value. So theta hat squared ml is going to be 1 over n squared double summation I equal to 1 through n, j equal to 1 through n, xi minus mu multiplied by xj minus mu. Here we have to deal with the two cases when I equal to j, I not equal to j, when I do the expected value, because the results are different. So this is 1 over n squared is common. Now we have I not equal to j, I goes from 1 through n, j goes from 1 through n. So you have expected value of xi minus mu, I'm sorry, squared here, squared, then expected, then xj minus mu. But if I is not equal to j, these two random variables are independent. So I can write here expected value of xj minus mu the whole square. So that's the break I get. Plus I equal to j. When I equal to j, there are such n terms. So then I equal to j, this becomes expected value of xi minus mu the sigma 4. So this is what we have to deal with. Notice this is easy. This is sigma squared. This is also sigma squared because that's by definition. And this is, you can look up you can check it out. This is 3 sigma 4. This is the fourth central moment. And so let me put all of them together, 1 over n squared. Notice that here there are such n squared minus n terms, n squared minus n multiplied by sigma 4, and here there are n terms. So this becomes n squared minus n plus 3n sigma 4 over n squared. So that becomes 1 plus 2 over n sigma 4. So let me substitute that, this result, I guess silly mistakes, this should be square here, which is what I have done. So I can substitute that here. So this is going to be 1 plus 2 over n sigma 4 minus sigma 4. So that becomes 2 sigma 4 over n. That's the variance of the maximum likelihood estimator. Notice that that also goes to 0 as n tends to infinity. So at least from what we have said, we can say that both the theta hat, mu hat ml and sigma squared hat ml are unbiased and consistent. In other words, the variance goes to 0 as n tends to infinity. I mean, in the second case, of course, in the first case, I don't need to know anything about sigma squared. Here I'm assuming that mu is known. All right, let me move on. And so that's it. So at least what we can walk away with from the Gaussian problem is that the two parameters, mu and sigma squared, the maximum likelihood estimators are unbiased and consistent. So those are nice properties. And more pleasingly, the maximum likelihood estimator for the mean is what we have been doing all the time. If you have a bunch of observations to get the mean, you add them up and divide by the total number of observations. So let me do a couple more problems. That's where you'll get an idea. Let's say xi are Poisson random variables and independent. So we make a bunch of observations, x1, x2, etc., xn. Each of them are Poisson. If you recall, before we move on, we'll say that Poisson has the property that mean and variance are the same, equal to lambda. But lambda here is unknown. So we look at the joint density function of x1, etc., xn. But this, since they being independent, you can also write this as the product of the marginal density functions. So each of them is what? E raised to lambda, lambda to the power xi over xi factorial, I equal to 1 through n. x1 equal to small x1, etc., xn equal to small xn, which is what I have here. So if you do this, this is e raised to minus n lambda, lambda to the power sigma xi over xi factorial, I equal to 1 through n. So let me take the logarithm of the joint density functions. So from here you get e minus lambda. From here you get sigma xi, I equal to 1 through n. The whole thing multiplied by log lambda minus a summation log of xi factorial. Notice the last term is immaterial because when we take the derivative with respect to lambda, this doesn't contribute. But the first two terms contribute. So let me do that next, which is the derivative of lambda with respect to small lambda. So that's going to be minus n. Then from here, plus sigma xi, I equal to 1 through n over lambda. So we'll equate this to lambda hat ml. This is the maximum likelihood procedure equal to 0. So then we can read for lambda hat ml from here. So that's going to be x1 plus x2 plus etc. xn over n. In other words, again x bar. So question is, what is its mean and variance? So here you know that if x1, x2, etc., xn are Poisson, the sum of independent Poisson random variables is Poisson. So this is Poisson with parameter n lambda. So the expected value of sigma xi is n lambda. Variance of sigma xi is also n lambda. So we can use these two properties here. So expected value of lambda hat ml, you can see from here, is the expected value of xi, which is n lambda over n. So that's n lambda over n, that's lambda. So this is an unbiased estimator. I'll compute the variance here. So notice the variance of, we want the variance of this. So variance of lambda hat ml is 1 over n squared, variance of sigma xi. But sigma xi, you can see here, sigma xi is Poisson with parameter n lambda. So the variance of this quantity is n lambda divided by n squared. So that's lambda over n. And that goes to 0 as n goes to infinity. So once again, this is also nice. This is also a consistent estimate. And finally, let me take something else. Let me take something arbitrary. Let's consider random variables with consider random variables which have this density function. So it goes something like this. This is a Rayleigh. If you put theta equal to sigma squared, that's Rayleigh. But in any case, just treat it as it's a non-negative random variable. Only takes positive values, whatever the physical interpretation. Let's say you have this family. Again, you have observations x1, x2, xn independent. So the question is, what is theta? From here, from the data, you need to compute the theta. So we will again go for the maximum likelihood estimator. So we look at this. So this is going to be logarithm of f of x1, etc., x and theta. So that's logarithm of the product of the density functions. Each one is given. So if I substitute, that's going to be logarithm of product xi over theta to the power n e raised to minus sigma xi squared over 2 theta. So when I take the logarithm of this, I get product of xi, which is not consequential, minus n log theta minus sigma xi squared over 2 theta. So I'm going to take the derivative of this quantity with respect to theta. So I get minus n over theta plus sigma xi squared, which is a constant over 2 theta squared. Theta equal to theta hat ml. We equate this to 0. So we have to solve this equation. So if you take this to the other side and cancel 1 theta, you can see you get, so this is where we are going to start. Theta hat ml turns out to be 1 over 2n sigma xi squared. From here, so sigma xi squared, n comes here, 2 is here, so that's what we get. So now the question is, what is its mean and variance? So we want expected value of theta hat ml. That's 1 over 2 and sigma xi I equal to 1 to 1 sigma xi squared. So we want to compute this quantity. So let's compute that quantity. Xi squared is integral xi squared ff xi dx 0 to infinity. So that's going to be 0 to, from the density function, x cubed over theta e raised to minus x squared over 2 theta d theta. Instead of writing xi, I just wrote variable x. So let me substitute x squared over 2 theta to be y, so that x dx over theta becomes dy, right? 2 cancels. So here you have an x squared is 2 theta y. So notice that when I substitute all this x squared becomes 2 theta y, and then you have x, this is dx, x dx over theta, x dx over theta is dy, so e raised to minus y dy. So this is 2 theta, y x goes to 0 to infinity, y the same thing, so 0 to infinity y e raised to minus y dy. This you can do by parts, that's one. So the answer is 2 theta. And if you substitute it here, this becomes 2n theta divided by 2n. So that's theta. So this estimator is unbiased, also unbiased for theta. So now the question is, what is its variance? So just to show you the dynamics, let me just do it. So the variance of theta hat ml is expected value of theta hat squared ml minus its mean squared. We just found out the mean. Mean is theta, so that's theta squared. So theta hat is here. So this is, if I substitute for theta hat, that's going to be 1 over 2n sigma xi squared. This is the theta hat ml is here, so I plug it in here and I have to square it again and then take the expected value minus theta squared. So when I square this, this becomes 1 over 4n squared outside. Here I get expected value of double summation xi squared xj squared. I equal to 1 through n, j equal to 1 through n minus theta. As before, we have to deal with two cases. I not equal to j, I equal to j. So that's 4n squared. Expected value of double summation I not equal to j xi squared xj squared plus expected value plus summation expected I equal to j. When I equal to j, this becomes xi to the power 4. I equal to 1 through n and minus theta squared. So here we can do one more simplification, 4n squared. When I is not equal to j, these two random variables are independent. So you have this, you can write it as the summation expected value of, so there are such n into n minus 1 random variables. So you have double summation I not equal to j xi squared expected value of xj squared. Each of them we found out somewhere. Expected value of xi squared we found out somewhere to be 2 theta. So each of this is 2 theta, plus we have to deal with this term, which we will do soon, xi to the power 4 I equal to 1 through n plus minus sigma squared. So let me just copy this onto the other side. So remember, here you get n into n minus 1 multiplied by 4 theta squared, this term. So we have variance of theta hat ml is 1 over 4n squared n multiplied by n minus 1 4 theta squared plus we have to deal with this term I equal to 1 through n expected value of xi to the power 4 The whole thing minus theta to the power 4, I guess. I might have made a mistake here. Let's see. Theta squared, I'm sorry. So you can already see, let me simplify this one more time. Notice that when I expand, you have n squared 4 theta squared. So 4n squared cancels, giving theta squared minus theta squared. So the only term here remaining is minus 4 cancels, minus theta squared over n, that's so far, plus summation I equal to 1 through n expected value of xi to the power 4. So let me compute this. So expected value of xi to the power 4 is integral x4 fx xi dxi. So that's x4, then x theta as before, e raised to minus x squared over 2 theta squared dx, 0 to infinity. So the same substitution, I'm going to put x squared over 2 theta squared to be y, so that x squared is 2 theta squared y, and this gives us x dx over, not 2 theta. That's the PDF. The PDF was xi squared over 2 theta, so I just have x dx over theta is dy. So if you substitute all this 0 to infinity, x goes to 0 through infinity, y also goes 0 through infinity. So notice we have x, this is x squared the whole squared. X squared is 2 theta y, so that's 2 theta squared y squared. Then you have x dx over theta, that's dy, and this is e raised to minus y dy. So this is 4 theta squared, integral 0 to infinity, y squared e raised to minus dy. Now, if you do this just a tiny integral, this answer is 2. So that's 8 theta squared. All right, here I missed a 4n squared, so there should be also a 4n squared here. So let me substitute. Each of this is now 8 theta squared. So this comes out to be minus theta squared over n plus 1 over 4n squared. Then you have n such terms, so there is an n here, then 8 theta squared. So n cancels, 4 cancels, giving 2. So the answer turns out to be theta squared over n, if I did it correctly, and that also goes to 0. In other words, so for this problem also, it's a consistent estimate. So you may say at this point, maximum likelihood, everything seems to be consistent. So let me show you a case where that's not the case. So let's take x1, x2, etc., xn to be uniform with random variable. It's some theta. So these are the observations, data. So the density function is known to be uniform, but the problem is we just don't know what this value is. So this happens a lot of times. You can sort of guess that you have no reason to believe the PDF is skewed in any fashion. So you assume it to be uniform, except the upper bound is you just have to guess the number of taxis in a town or whatever, somebody's wealth, etc., etc. In a uniform population, the maximum office salary, and so on. But if you get a bunch of observations, question is what's the maximum likelihood estimate? So let me first of all represent the joint density function here, x1, x2, etc., xn is 1 over theta n, because all of them are independent, is product of f of xi So that's this, but provided xi is between 0 and x1 is between 0 and theta, etc. xi is between 0 and theta, etc. So all this you can write this as minimum of x1, x2, etc. xn is greater than 0, and the maximum of x1, notice each of them are less than theta, so the maximum of x1, x2, etc. xn is also less than theta. So I can write all this using an indicator function as 0 comma min. In other words, the variable is, remember the variable here is theta, theta is the unknown, minimum of xi, and another indicator function theta comma maximum of xi. In other words, this is only valid if between this. Okay, so this is the L function. So let's draw the L function. Remember, these are data. Unknown is theta. So as a function of theta, I'm going to draw the L function. So it says here, so question is, remember the parameter is theta. It says theta is greater than maximum. So whatever is the density function, it's only beyond this value. So if I denote this as max of xi, at that value, I plug in theta. Theta is this. I plug it in here. So it's going like in this fashion. That's the going as 1 over theta from this point onwards. And the principle of maximum likelihood, we are looking for the maximum value of this likelihood function. The theta corresponding to that is this one. So we get theta hat ml in this case is max of x1, x2, etc., etc. So you can see that's a non-linear estimator. So the question is this an unbiased estimator? So let's try to do that also. So again, for when the unknowns are uniform with an upper limit that's unknown, then the maximum likelihood estimator for that unknown is the max of x1, x2, etc., etc. All right, so let me call that y to be max of x1. Now it is coming back to, so this is your maximum likelihood estimator. We want its mean and variance, let's say. So we need to find out the density function of y. So I'll start with the distribution is probability of y less than or equal to y. But y is given to be max of x1, etc. So this is a problem in probability. If maximum is less than y, each of them must be less than y. But these are all independent random variables, so this is the same as probability of any xi is less than or equal to y. But this is, all of them are identical, so that's just a probability of any one of them, xi is less than or equal to y. But that's nothing but the area from 0 to y, 1 over theta. That's a density function of x. So this comes out to be y over theta, so that's yn over theta n. Y, of course, y is maximum. Each one goes from 0 to theta, so that's the density function. So now we can find out expected value of theta hat ml. That's expected value of y. So that's y f y y dy. Y goes from 0 to theta. So let me substitute this function. So this is 0 to theta yn multiplied by yn plus 1 over theta n dy. So you have expected value of theta hat ml turns out to be yn plus 2 divided by n plus 2, 1 over theta n. No, I'm sorry, I made a mistake here. So this is the distribution function, and the density function is the derivative of that. So this we need to find out so the derivative of this is going to be n minus 1 over theta n. So this will be just there will be an n minus 1. This will become, so it will be just this. So notice that the density function here will be n y to the power n minus 1 over theta n y between 0 and theta. So when you substitute that, expected value of theta hat ml turns out to be integral 0 to theta n yn over theta n dy. So that's n over theta n yn plus 1 over n plus 1 0 to theta. So that's theta n plus 1 and n plus 1 theta n. So this turns out to be n over n plus 1 over theta. So it's certainly not equal to theta. So it's not an unbiased estimator. It is not an unbiased. But you may say, all right, so this is a constant. I can flip the constant and make it an unbiased estimator. Then it won't be the maximum likelihood estimator. So the point is the maximum likelihood estimator here is not unbiased. But if you look at n plus 1 over n multiplied by theta hat ml, this will be an unbiased estimator. But that's not maximum likelihood estimator. In this case, that was easy because just the bias turned out to be a constant. All right, so now we can, if you want, you can proceed to find the variance of the maximum likelihood estimator. So remember, we have defined the y to be theta hat ml, and fy was n over theta n y to the power n minus 1, and expected value of y we found out to be n over n plus 1 theta, which also is the and now we want expected value of y squared. So that's going to be y squared fyy dy 0 to theta. So that's n over theta n from here, yn plus 1 dy 0 to theta. So that's n theta n plus 2 over n plus 2 theta n. You take the derivative and substitute 0 and theta. So that comes out to be n theta squared over n plus 2. So the variance of maximum likelihood estimator, which is the same as the variance of y, is expected value of y squared minus its mean squared. Mean is here, expected value of y whole squared. So let me substitute all the values. We have n theta squared over n plus 2 minus here n over n plus 1 the whole squared theta squared. So if I substitute, so I have n plus 2, n plus 1 the whole squared. Here you have n plus 1 the whole squared minus n multiplied by n plus 2 multiplied by theta squared, I guess. Multiplied by n. So notice that when I expand this, I get n squared cancels, 2n cancels, then I have 1. And so that's it. So the answer will turn out to be, if I did it correctly, n theta squared over n plus 1 the whole square multiplied by n plus 2. Also, this also goes to 0 as n goes to infinity. So to summarize, expected value of theta hat is n over n plus 1 theta. So that's not unbiased. And its variance of theta hat ml is n over n plus 1 the whole squared multiplied by n plus 2 theta squared goes to 0 because more n cubed essentially. This is 1 over n, roughly this goes as theta squared over n squared. Now if you want an unbiased estimator, also we can find out. It won't be maximum likelihood estimator. So if you define z to be, as I said, n plus 1 over n multiplied by y, you can see expected value of z is, remember this is y, theta hat ml is y. Expected value of z is theta, so we have an unbiased estimator for theta, and the variance of z is the constant n plus 1 squared over n squared multiplied by the variance of y, which is theta hat ml. So if I substitute it here, this becomes 1 over, also goes to 0. So whichever, if you want an unbiased estimator, you pick this. If you want an ML estimator, it is this. ML estimator is not unbiased, but its variance goes to 0. So you can show that all ML estimators have this asymptotically this property. In other words, the variance goes to 0. So I showed you 3-4 examples here. And if you can, sometimes you can play games like this and create an unbiased estimator. So ML motivates to sort of give you some ideas. So it's very close to ML, but unbiased. And here is, and that is also consistent. In other words, variance goes to 0. So there are more to it, but I'll stop here as an introduction to maximum likelihood estimator.